Okay, I want you to just picture something for a second. Look around the room you're in. You see the walls, the floor, maybe a window. You feel time passing. You treat these things, three dimensions of space, one of time, as like the absolute reality.
Right. It's how we survive, certainly. It's our intuitive model of the world.
Right. But what if all of that is just a slice, a shadow? What if the real action is happening in a five-dimensional structure and we're just seeing a projection of it? And here's the kicker. What if the math for this doesn't come from some tenured professor at Harvard, but from an anonymous enthusiast who taught themselves tensor calculus by watching YouTube videos?
It really does sound like the premise of a sci-fi novel, doesn't it? The classic outsider cracking the code trope. But today we are looking at something very real. We have a stack of 3 draft papers here by someone identified only as A author 1.
The titles alone are a mouthful. We've got a split quaternion, like extension of the complex plane, then the Lorentzian cosmological model, and cosmological evolution of Lorentzian spacetime. It sounds super heavy, I know, but the mission for this deep dive is actually pretty exciting. We're going to see if this author has managed to build a bridge between the two things in physics that notoriously hate talking to each other, special relativity and quantum mechanics.
That is the holy grail of physics, unification. And this author is proposing a model called space-time ultra.
Space-time ultra, I like the name.
Yes. Despite the flashy name, the ambition here is serious. The author tries to construct a universe model where gravity, the expansion of the cosmos, even the fundamental equations of quantum mechanics, they all just naturally emerge from a single geometric assumption.
So they're not adding these forces in like ingredients to a recipe?
Not at all. They're suggesting that if you build the mathematical stage in a certain 5D way, the actors, gravity, and quantum fields just appear on their own.
That is a massive claim. So, okay, let's unpack this. We have to start where the author starts. The math. Now, I remember high school algebra. I remember imaginary numbers. The square root of -1. I times I equals -1.
Exactly. That's the basis of the standard complex plane. You have your real numbers and you have imaginary numbers. It creates this circular geometry, which is great for things that rotate. But the author begins the first draft by asking a completely different question. They ask, what if we create a number system where the imaginary unit, let's call it, what if L multiplied by itself equals +1?
So L times L is 1. Why does that change anything? I mean, it seems like such a tiny tweak.
It changes the geometry entirely. In standard complex numbers, you get circles. In this system, because L squared is +1, you get hyperbolic geometry.
Hyperbolic.
Think of a saddle shape instead of a sphere. And why does this matter? Because the geometry of special relativity, the way Einstein described how space and time mix together, is hyperbolic. By changing just that one definition, the author is building a calculator that speaks the language of relativity right from the start.
Okay, I think I'm with you. So they aren't just using standard numbers. These are called split quaternions, right?
Correct. And it gets a little more complex from there. They don't just use one new variable. They build a whole basis set: 1, L1, L2, and L3.
I have these vague memories of quaternions being a nightmare because you can't just multiply them in any order you want.
That is the key feature. It's what we call a non-commutative ring. If you multiply L1 by L2, you get a different result than if you multiply L2 by L1. In fact, the anti-commute.
Anti-commute.
One result is the negative of the other.
That just seems messy. Why would you ever want a math system where A times B doesn't equal B times A?
Because nature has direction. But more importantly, for this paper, this specific algebra lets the author define a squared length for any vector. And because of the way these lay units interact, that squared length can be positive or negative.
Oh, wait a second. A negative length? I can't be -6 feet tall.
In physical space, no. But in space-time physics, this is totally standard. We call it the interval. If the result is positive, the math classifies it as time-like. If the result is negative, it's space-like.
So time-like means it's related to time, and space-like is distance.
Roughly, yes. Time-like means events are close enough that a signal could actually travel between them. Cause and effect. Space-like means they're too far apart. Even light couldn't get from one to the other in time.
And the author's math just spits this distinction out automatically.
That is the first big aha moment in the text. This structure, these split quaternions, they perfectly mimic something called the Minkowski metric.
Which is the mathematical backbone of Einstein's relativity.
Exactly. Before the authors even started talking about the universe or planets or atoms, they have built a mathematical toolkit that naturally produces the rules of special relativity. They set up a geometric stage where Einstein's laws just feel at home.
Okay, so we have the stage, now we need the action. In the second section, the author introduces a transformation. They use the symbol lambda. And this, I think, is where we make the jump to the fifth dimension.
This is the absolute core of the space-time ultra concept.
Mm.
The author posits that our 4D space-time, time plus the 3 dimensions of space, is embedded in a 5-dimensional structure. And to make this work, they introduce a very specific variable. The papers just refer to it as V.
Just the letter V.
Yep, the ultra speed.
Ultra speed. Okay, it sounds like something a superhero has. What is V actually representing in this model?
It's the master parameter. These papers, V isn't a constant. It's a function of time, t. The author describes V as growing monotonously from 0 to 1 over the entire age of the universe.
So at the moment of the Big Bang, this V is 0. And eventually, billions of years down the line, it approaches 1.
Precisely. And this V acts as a kind of scaling factor. The author shows that if you apply this lambda transformation, the metric tensor, which is really just the grid we use to measure distances in spacetime, it starts to depend on V.
Let's visualize that. How does the grid actually change?
It's an inverse relationship. The time component of the metric scales by -1 divided by V, and the space components, they scale by just V.
So as V gets bigger, space is scaling up.
Yes, space expands.
But time is being divided by V.
Exactly. So as V grows, the time component behaves very differently than the space components.
It's almost like a lens. Imagine a film projector. The ultra-speed V is like the zoom lens. As you slide V from 0 to 1, you are physically stretching the image on the screen. That's space expanding, but you're also kind of messing with the frame rate, the time.
That is a very helpful analogy. It changes the resolution of the universe over time. By making the metric dependent on this evolving V, the author is setting up a universe that naturally expands. They don't need to push it. The geometry itself is sliding open.
But it gets weirder. We promised a fifth dimension. Just saying we embedded it isn't enough. In the second draft, the Lorentzian cosmological model, the author talks about a curled-up dimension.
Right. This is where the author tries to reconcile their geometric model with general relativity. In general relativity, a vacuum-empty space is supposed to be Ricci-flat.
Ricci-flat, that means no curvature.
It means no matter-induced curvature. The author wants to force their math to be Ricci-flat to show it's a stable solution. And to do that, they introduce an extra dimension, let's call it W, but it's not an infinite highway like the other dimensions, it's compactified.
Rolled up.
Exactly, like a drinking straw. From a distance, a straw looks like a line one-dimensional. But if you're an ant crawling on it, you can walk around the circumference. That little circle is the extra dimension. The author suggests this W dimension is rolled up into a circle with a radius r.
And this leads to a term in the paper that sounds like a thriller movie title, the killing ansatz.
It does sound dramatic, doesn't it? But Wilhelm Killing was a mathematician. A killing vector just describes a kind of symmetry, a direction in which a space looks the same.
Oh, okay, that makes more sense.
So the author defines a time-like killing ansatz.
In English, please.
Essentially, they're just putting a constraint on the math. They're saying that the radius of the universe and the behavior of this extra curled-up dimension have to depend on V in a very specific way. They're linking the geometry of the extra dimension to the expansion speed.
It feels like a lot of hoop jumping. Why go to all this trouble with curled up straws and killing vectors?
Because of the payoff. And this is, in my opinion, the most startling result in the entire stack of papers.
Okay, I'm ready. What's the payoff?
The author takes this weird 5D time-dependent curled-up metric, and they apply something called the box operator to it.
The box operator. That's the D'Alembert-Shin, right? The wave operator.
Correct. It's the standard mathematical tool to see how a field propagates, how it waves through space-time. Usually, if you do this in flat space, you get a simple wave equation. But the author applies it to a scalar field inside this space-time ultrametric.
And what happens?
They crunch the numbers using tensor software, thankfully, and it spits out an equation. And that equation looks exactly like the Schrödinger equation.
Wait, the Schrödinger equation, the heart of quantum mechanics, the thing with the cat.
That is the one.
But how, I mean, they started with geometry, they started with a 5D shape expanding. How do you get quantum physics out of just shape and speed?
That is the author's central claim. The equation they derive contains terms that function exactly like effective mass and effective potential. But these aren't just random constants of nature. In this model, mass is derived from the expansion speed v and the winding number of that extra dimension.
So if I'm understanding this right, In this model, mass isn't just some property a thing has. Mass is a geometric effect of the fifth dimension.
Correct. Specifically, the math shows the effective mass depends on v squared times n over r. So as the universe ages and v changes, the very properties of matter itself, the way it waves and behaves, are being dictated by the geometry.
That is absolutely mind-blowing. We've spent 100 years trying to glue general relativity and quantum mechanics together, and this paper is basically saying they aren't two different things, they're just what happens when you view a 5D structure from the inside.
It suggests that what we perceive as quantum weirdness might actually just be the shadow of that extra dimension.
But does it match reality? I mean, you can write beautiful math that describes a universe that doesn't exist. Does this space-time ultra look like our universe?
That brings us to the third draft, cosmological evolution. Here, the author puts the model to the test against actual cosmology.
They use the Friedman equations, right?
Yeah,
Those are the big ones for the Big Bang.
the gold standard. The author plugs their specific metric, the one with the scaling v, into the software. The software calculates the Einstein tensor, and from that they derive the density, rho, and the pressure, p.
Yeah.
And the form is almost identical to the standard Friedman equations used by NASA and every astrophysicist. In this model, the density and pressure of the universe are driven by the first and second derivatives of v.
Meaning the stuff in the universe is being described by how fast that v parameter is changing.
Exactly, the rate of change and the acceleration of v.
So let's look at the timeline. At time 0, v is 0. Then it grows. The author talks about a slow exponential curve, 1 minus e to the negative lambda t.
And this curve is crucial. At the very start, v changes rapidly. That mimics cosmic inflation. Then, as time goes on, v flattens out and approaches 1. The author claims that if you plot this curve, the scaling factor of the universe qualitatively matches the standard lambda CDM model.
Lambda CDM, that's the concordance model. It's our current best picture of the universe, but it requires dark energy and dark matter to work, right?
Right. And the author's basically saying, I didn't put dark energy in by hand. I didn't add a cosmological constant. I just defined how v moves from 0 to 1, and the geometry naturally produces an expansion that looks like it's being pushed by dark energy.
It's deriving dark energy from the geometry of the ultraspeed.
It's a unification theory. It attempts to explain the very big cosmic expansion and the very small quantum mass using the exact same mechanism.
We have to talk about the human element here. We mentioned this person is an outsider. Section 5 of our breakdown highlights this. These are not polished papers from Nature or Science.
No, and the author is refreshingly transparent about that. In the special thanks and introduction sections, they explicitly state, I do not exercise a research position. They actually apologize for missing references because they literally cannot afford the paywalls to read current academic papers.
They mention learning the math from YouTube content creators.
Which is remarkable and honestly a sign of the times. But here is the thing. The math checks out. They used Repiex Maxima.
That's a computer algebra system.
Yes, and this is significant. Tensor calculus is notoriously difficult. If you do it by hand on a chalkboard, you will drop a minus sign or mess up an index. It happens to the best of them. But by coding the metric into the software, the author ensures the derivation is consistent. The software performs the derivatives.
So they didn't just scribble on a napkin. They built a piece of code to verify their logic.
Exactly. The derivation of the continuity equation, the structure of the Einstein tensor, these are really complex operations. The fact that the software outputted recognizable standard physics equations from this novel input, it suggests a high level of competence. The author might be an outsider, but they're using professional-grade logic.
It really makes you wonder. We have this image of the genius in the ivory tower, but how many ideas are just stuck in draft PDFs on someone's hard drive because they don't have the credentials to get published?
It's the Ramanujan problem all over again. History is just peppered with people who saw patterns the establishment missed. This might be one of those cases, or it might be a beautiful mathematical curiosity that doesn't quite fit reality. But the fact that it coherently links relativity and quantum mechanics warrants a serious look.
So let's try to pull this all together. What do we actually have here?
We have a new number system, these split quaternions, that naturally creates the geometry of special relativity. We have a 5-dimensional embedding. We have a master variable, v, the ultraspeed, that dictates the scale of space and time.
And this variable v, as it slides from 0 to 1, drives the expansion of the universe, matches the lambda CDM curve, and perhaps most crazily, forces scalar fields to obey the Schrödinger equation. It derives gravity and quantum mechanics from the same source.
That is the summary. It's a unification theory based on the idea that our 4D reality is just a moving slice of a 5D structure.
So what does this all mean for us? Why should you, the listener, care about a draft paper by some anonymous math enthusiast?
Because it challenges our assumptions about complexity. We often assume a unified theory of everything will be hideously complex, requiring thousands of pages of new math that almost no one understands. This model suggests that if you just change your perspective, if you look at the universe from 5 dimensions instead of 4, and if you allow the speed of time to change, then complex phenomena like quantum mass and cosmic expansion might just be simple geometric shadows.
It suggests the universe might be simpler than we think, just viewed from the wrong angle.
Precisely. And it validates the scientific method itself. It doesn't matter who you are or where you learn math. If the equation balances, it balances.
Here's where it gets really interesting for me. I keep thinking about this ultra speed V. The author treats it as the driver. It starts at 0 and goes to 1, but what happens if it hits 1?
The math gets very dangerous there. The scaling factor involves a term called gamma. In this model, gamma is 1 over the square root of 1 minus v squared.
Okay, math class flashback. If v is 1, then v squared is 1. 1 minus 1 is 0. We're dividing by 0.
Correct. Infinity. The scaling factor blows up.
So does the universe have a speed limit
Well,
or a hard expiration date?
if the model holds, yes. As v approaches 1, the scaling of space goes asymptotic. It suggests that what we perceive as time is just a side effect of us sliding along this geometric curve. We are just passengers on the ultra-speed trajectory.
And the end of the universe is just the moment the slider hits the top.
It's a provocative thought. If v is the fundamental driver, then time isn't a flowing river. It's a measurement of how far v has progressed from 0.
I love that image. We're just surfing the wave of v.
And hopefully the math holds up so we can understand the ride.
Exactly. It's a reminder to keep an open mind. The next Einstein might not be at Princeton. They might be in the comment section of a math tutorial, uploading a PDF that rewrites the laws of the universe.
It is entirely possible.
If you want to check out the sources for yourself, check the show notes. Thanks for diving deep with us.
It was a pleasure.
Keep surfing the wave. We'll see you next time.